So in question number 4, you saw how your sums that you computed are related to the integral that you computed. And again, as we said on the previous slide, that relationship also goes the other way. That in addition to bounding an integral in between two sums, a left-hand sum and a right-hand sum, if you want to think of it in the Riemann sum formalism, we could do the opposite. We can bound a sum in between a left-hand integral and a right-hand integral. And the picture is the one that we have up here in the upper right. That if I have a sequence which is decreasing and positive, and as long as I can connect the dots with a continuous function, then I can bound the value of the sum, which is the sum of the areas of these rectangles in here. I can bound it, on the one hand, by an integral which connects the right-hand endpoints of those boxes. That integral is going to be bigger than the sum. And on the other hand, an integral which connects the left-hand endpoints of the boxes, which is going to be smaller than that sum. So if my question, for example, is how do I determine whether or not the series summation of 1 over n squared, starting from, let's say, n equals 4 to infinity, converges, then according to what we have up here, the integral which is definitely smaller than the value of our sum, the integral on the left here, is the one which connects the left-hand endpoints, which if I mark these left-hand endpoints as 4, 5, 6, and so on, then that's the integral from x equals 4 up to wherever, up to whatever our upper limit is. So the integral from 4 to n is going to be less than or equal to the value of the sum from n equals 4 to n. Meanwhile, if instead of the left endpoints, if I decided to connect the right-hand endpoints, then I really have to shift everything over by 1 and start my integral at 3 instead of at 4. So this is the technical aspect of what we call the integral test, that these partial sums can be bounded in between the integral on the left and the integral on the right. Both of them are integrals of the very same integrand, 1 over x squared. The only difference between them is their lower limit. It's 4 on this side, 3 on that side. But the irony of all this is that it is much easier to do calculus, namely compute the values of these integrals, than it is to do the sum of fractions that's in there in the middle. So let's do the calculus on the outsides. What's an antiderivative for 1 over x squared? Negative 1 over x. And then I'm just evaluating that from 4 on the bottom to n on the top, where n is whatever we'd like it to be. And then for my integral on the right, I've got the same antiderivative, and I have the same upper limit. I just have a different lower limit. So when I evaluate this, I end up with, on the left-hand side, I get 1/4 minus 1 over n, is what I get on the left-hand side. Let me just, it'd be negative 1 over n plus 1/4, right? 1/4 minus 1 over n. And on the right-hand side, I get 1/3 minus 1 over n. And in the middle, trapped in the middle in between these two, is the partial sum, I called it Sn, of my series. Now, how do we connect the partial sum to the value of the infinite sum? What do I have to do? What is the value of an infinite sum defined to be? It's the limit, as n goes out to infinity. So that's all I have to do here. I just have to take the limit as n goes to infinity of this side, and the limit as n goes to infinity of this side, and then the limit as n goes to infinity of the thing in the middle. But the thing in the middle, if I take its limit as n goes to infinity, the value I get, if it exists, is exactly the sum, n equals 4 to infinity, of 1 over n squared, whatever that happens to be. But I don't know that value. I can, however, know the values of the things on the outsides. What happens to 1/4 minus 1 over n as n goes to infinity? 1/4 minus 0, exactly. So the thing on the left is 1/4. Meanwhile, 1/3 minus 1 over n becomes 1/3. So this tells us something. If we look at this statement on the very bottom, First of all, what does it tell us about whether or not this infinite series converges? It converges, because its value is something between 1/4 and 1/3, so it doesn't blow up to infinity. Not only that, the sequence of partial sums is monotonically increasing, right? Every sum is larger than the one that precedes it. And any sequence which is monotonic and bounded, as this one is, must converge. That was one of the technical theorems that was in 10.1, I believe it was. Therefore, this infinite series converges. And we can answer this question, the initial question, in the affirmative. Yes, it converges. Not only that, we can also say for sure that it converges to something in between 1/4 and 1/3. It's not the greatest estimate in the world, so it's something between 0.25 and 0.333 repeating. But yet it still tells us a little bit more than we needed to know. Right? We only needed to know whether it converges. And we conclude the answer is yes, and it converges to something between 1/4 and 1/3. Now, what is the integral test? The integral test is exactly what we just did. Right? That by computing the values of these integrals and then letting the n go to infinity, we can determine whether or not the partial sums remain bounded as n goes out to infinity. So when we think of the integral test, usually what we think of doing is just taking our sum and turning that sum into an integral, and then just evaluating that integral, but letting the upper limit of that integral look like infinity instead. That makes this integral an example of something called an improper integral, something about which I've asked you to read and watch videos over the course of this evening. Because the techniques of taking improper integrals are exactly what we just did, right? We have an upper limit which we like to think of as being infinity, but really it's just some number n, which is arbitrary. We evaluate the antiderivative, and then we let n tend toward infinity to find the value of that improper integral. But the integral test then tells us that if the improper integral converges, then both the blue and the red integrals here are going to end up being finite numbers, and therefore my series is going to end up converging. On the other hand, if the improper integral does not converge, if the improper integral gives me infinity, then both the blue and the red things are infinite, and therefore the value of my infinite series must also diverge and be infinite. So the integral test just says the series does whatever the integral does, as far as converges or diverges. And we're going to pick up that ball tomorrow morning.